All right, let's dive into one of the biggest, most mind-bending ideas in all of physics, the true shape of gravity. See, Albert Einstein didn't just tweak the old rules. He tore them up and started over. And what he found is so much weirder and, honestly, so much more beautiful than that simple force we all learned about in school.
So, right off the bat, let's just throw a crazy idea out there. We all feel gravity, right? It's what keeps our feet on the ground. It holds the planets in their orbits. It feels like a force, like a pull. But what if it isn't? What if it's something much deeper? Something literally woven into the fabric of reality itself? Okay, so if it's not a force, then what in the world is it? Well, Einstein's incredible answer was that gravity isn't a pull through space. It's the actual shape of space. Let's dig into how he completely reimagined gravity as pure geometry. Now, don't let the math on this slide intimidate you. This single equation is the beating heart of general relativity. Just look at the idea behind it. On one side, you've got all the stuff in the universe, matter, energy, everything. And on the other side, you have the geometry, the shape of space-time. What Einstein figured out is that these two sides are equal. They're not just connected, they're two ways of saying the same thing. So matter doesn't create a force. It literally tells space-time how to bend and curve. But hang on, that brings up a huge problem. If we're living inside this curved reality, kind of like fish swimming in a warped fishbowl, how could we ever possibly know it's curved? It's a real puzzle. So let's see how physicists figured out a way to spot this invisible shape. Here's the tricky part. Imagine you're an astronaut floating in orbit around the Earth. You're in what's called free fall. You feel totally weightless, right? From your perspective, everything seems perfectly normal, perfectly flat. There's no obvious sign that you're actually hurtling along a massive curve in space-time created by our planet. So just watching one person or one object isn't going to cut. It really is a brilliant riddle, isn't it? How do you measure a shape you can't see from a point of view where you can't even feel it? Well, it turns out the solution is even more clever than the problem itself. And here's the secret. You have to stop looking at just one thing. You can't see the curve by watching a single falling apple. But if you watch a whole cloud of apples and you precisely measure how they move in relation to each other, that's when the hidden shape of space-time starts to give itself away. And this shows it perfectly. Let's say you're in a little lab that's freely falling, and you release a perfect sphere of dust particles. Now, if space were flat, they just float there in that sphere shape. But since you're falling towards a planet, something amazing happens. The particles closer to the planet get pulled just a tiny bit stronger and move ahead, while the particles on the sides get pulled inwards toward the center. And that perfect sphere gets distorted. It stretches into an ellipse. That stretching and squeezing, that's the smoking gun. That's the proof of curved spacetime. Now, this whole stretching and squeezing effect has an official name: tidal gravitational forces. But here's the key thing. Don't let that word force trick you. It's not some new kind of pull. It's the physical, measurable result of space-time curvature. When you measure a tidal effect, you are, quite literally, measuring the geometry of the universe. And believe it or not, you see this exact same thing happening every single day. The ocean tides, they're caused by this very principle. The moon's gravity pulls on the side of the Earth closer to it a little bit stronger than it pulls on the center, and it pulls on the center a bit stronger than the far side. This difference in pull stretches our oceans into two bulges. So yeah, the tides are direct proof of space-time curvature, happening right here on our own planet. So we can actually see the curve's effect on our oceans, which is amazing. But how do physicists describe it with any precision? Well, that takes a whole new kind of mathematical language. One that was basically designed to map out the geometry of our universe. The fancy name for what we saw with that cloud of dust is geodesic deviation. A geodesic is just the straightest possible line you can draw through space-time. Now, in flat space, if you have two parallel lines, they stay parallel forever. But on a curved surface, like the Earth, think about two lines that start out parallel at the equator, both heading north. They eventually cross at the North Pole, right? Geodesic deviation is the math that measures that exact convergence or divergence, and in doing so, it reveals the local curvature. I love this table. It's basically a Rosetta Stone for translating Newton's physics into Einstein's. On the left, you've got familiar stuff like Newton's law of motion. Then look to the right. That same idea becomes the geodesic equation, which just means following the straightest possible path through curved spacetime. And here's the big one. What Newton called tidal forces, Einstein's theory reveals is actually Riemann curvature, the real mathematical description of spacetime's shape. It's a brand new language for describing the very same universe. So at the very core of all this math is something called the Riemann curvature tensor. Yeah, the name sounds pretty scary, but just think of it like a complete instruction manual for gravity at any single point in space. You can ask it, hey, what happens if I'm falling this way and my friend is falling that way? And it'll give you a precise answer, telling you exactly how much you'll be stretched apart or squeezed together. It holds all the local secrets of the tidal forces.
Okay, now that we have the tools, let's take them for a spin, shall we? Where in the universe can we find the most warped, the most twisted, the most extreme examples of spacetime curvature? The answer, of course, is near a black hole.
Okay, so the textbook sets a pretty vivid scene here. You've been captured by space pirates, and their method of getting rid of you isn't walking the plank. No, they're dropping you into a black hole. What happens next is a direct and terrifying result of everything we've just been talking about. As you fall, the curvature of spacetime gets insanely intense. Those same tidal effects we saw gently distorting that dust cloud, they go into absolute overdrive. The curvature at your feet would be so much stronger than at your head that you'd literally get stretched like spaghetti. At the same time, the curvature at your sides would be crushing you inwards from all directions. And just to put a number on it, the source material estimates that the tidal force pulling you apart would be somewhere around 10 to the 9 newtons. That is the equivalent weight of about 100,000 tons. That is the ultimate, terrifying power of curved spacetime. But the story doesn't stop with static curves. No way. If spacetime is this dynamic fabric, then it can do more than just bend. It can ripple. When truly massive objects, like two black holes, spiral into each other and collide, they send out gravitational waves, which are actual tremors in the geometry of space and time itself. And this wasn't just some wild idea Einstein had. Decades before we could ever dream of detecting them, the math told him they had to exist. That equation you see on the slide is a classic wave equation. It made an absolutely stunning prediction. Gravity doesn't travel instantly like Newton thought. It has to travel in waves at a finite speed, the speed of light. So the next time you feel that familiar tug of gravity, don't just think of it as a pull. Think of the actual shape of the universe gently holding you in place. And just remember, at this very second, invisible ripples from distant colliding black holes are passing right through your body, carrying the stories of the cosmos. We are all, quite literally, swimming in an ocean of spacetime.